There are more stars in the observable universe than grains of sand on every beach on Earth. Planets orbit most of them. The chemistry of life is scattered everywhere. And yet, in over 60 years of searching, across every frequency we know how to listen on, the universe has returned nothing but silence. Most people assume the answer is simple. Either nobody's out there or we just have not looked hard enough. Both of those are wrong. The real reason alien contact may never happen has almost nothing to do with whether life exists. It has everything to do with the structure of reality itself. Distance, time, physics, and fragility do not just make contact difficult. They may make it permanently impossible, even in a universe overflowing with life. If this kind of deep science keeps you thinking long after the video ends, a like and a subscribe go a long way. It helps us keep making these, and we genuinely appreciate every single one of you who shows up for this. Are you comfortable? Let's begin. Start with a number. 2 trillion. That is the current best estimate for how many galaxies exist in the observable universe. 2 trillion galaxies. Some are dwarfs containing only a few billion stars. Others are giants holding several trillion. Our own Milky Way sits somewhere in the middle, with an estimated 200 billion to 400 billion. Each of those stars burning for millions or billions of years. Many of them, perhaps most of them, surrounded by planets. For most of human history, we had no way to confirm whether planets existed around other stars. We suspected. We imagined. We wrote stories about it. But we did not know. Then, in the 1990s, astronomers detected the first confirmed exoplanet orbiting a sun-like star, and the floodgates opened. The Kepler Space Telescope, launched in 2009, found thousands of confirmed planets in one small region of one arm of one galaxy. The conclusion from that data changed everything. Planets are not rare. They are everywhere. On average, every star in the Milky Way has at least one planet. The total number in our galaxy alone is estimated to be in the trillions, and a significant fraction of those, billions by most calculations, sit in the habitable zone of their star, the orbital region where temperatures could allow liquid water to exist on the surface. Billions of potentially habitable worlds in one galaxy. 2 trillion galaxies in the observable universe. The raw numbers are so large that the human brain has no mechanism for truly comprehending them. The universe is not just big. It is built on a scale where the word big loses all meaning, and those numbers create a question that has haunted science for over 70 years. If the universe is this rich, this old, this saturated with the raw ingredients for life, then where is everybody? That question did not begin in a laboratory or a research paper. It began over lunch. In 1950, a group of physicists at Los Alamos National Laboratory sat down to eat. Among them was Enrico Fermi, one of the most brilliant minds of the 20th century. The man who built the first nuclear reactor. A Nobel Prize laureate whose intuition for physics was legendary. The conversation that day had been casual, drifting from newspaper cartoons about aliens to flying saucers. And then, in the middle of the meal, Fermi went quiet. He looked around the table and asked a simple question. Where is everybody? His colleagues stopped chewing. They understood immediately what he meant. The galaxy is roughly 13 billion years old. Many of its stars are billions of years older than ours. If even a small percentage of those stars produced planets where intelligent life developed, some of those civilizations would have had an enormous head start on us. millions of years, possibly billions. That is enough time to develop technologies we cannot even conceive of. Enough time to spread across the galaxy many times over using nothing faster than a fraction of the speed of light. Fermi did some rough calculations in his head. The numbers did not work. Even with deeply conservative estimates, the galaxy should show signs of habitation, signals, structures, artifacts, waste heat from massive engineering, something. And yet the sky was clean. No signal had ever been confirmed. No structure had ever been found. No artifact, no probe, no ruin on any moon. No strange shadow blocking distant starlight. Nothing. That contradiction between what the numbers predict and what observation reveals became one of the deepest unsolved problems in all of science. It was eventually named the Fermi paradox. And the word paradox is important. It does not mean mystery. It means contradiction. The math says they should be out there. The evidence says they are not. Both things cannot be true at the same time. And that gap between expectation and reality has driven scientists, philosophers, and dreamers to propose hundreds of explanations over the decades since that lunch. But before we examine the answer this story is building toward, we need to understand why the expectation of contact is so strong in the first place. Because the assumption that aliens should be reachable is not just a casual hope. It is woven into the mathematics, the culture, and the intuition of an entire species. In 1961, a young astronomer named Frank Drake sat down at the National Radio Astronomy Observatory in Greenbank, West Virginia. He had organized a small gathering of scientists to discuss one enormous question: how many intelligent civilizations might exist in our galaxy right now? To guide the conversation, he wrote a formula on a chalkboard. It was never meant to give an exact answer. It was meant to organize the problem into steps that could be studied one at a time. That formula became known as the Drake equation. The idea is straightforward. Start with the rate of star formation in the galaxy. Multiply by the fraction of those stars that have planets. Then the fraction that could support life. Then the fraction where life appears. Then the fraction where it becomes intelligent. Then the fraction that develops detectable technology. And finally, multiply by how long those civilizations last before going silent. Each step seems reasonable on its own. And that is what makes the result so striking. Even using cautious numbers, conservative estimates that deliberately lowered every variable, the equation kept producing answers in the thousands. Thousands of civilizations in the Milky Way right now, at this moment, potentially detectable if we pointed the right instrument at the right patch of sky. Some estimates went much higher, tens of thousands, hundreds of thousands. The galaxy, according to the arithmetic, should be alive with chatter, beacons flashing from distant worlds, accidental radio leakage drifting between stars, evidence of engineering on scales we can barely imagine. And yet, when we pointed our telescopes at the sky, we heard static. We saw nothing out of place. The math said the universe should be crowded. The universe said otherwise. Now, here is the catch. The Drake equation is only as strong as the numbers you feed into it. And in 1961, most of those numbers were guesses. We did not know how many stars had planets. We did not know how often life begins on a world where conditions allow it. We had exactly one example of intelligent life developing, us, and we did not understand how it happened. The equation was not a calculator. It was a framework for organized ignorance, a way to map what we still needed to learn. But the expectation of contact was not confined to a formula on a chalkboard. It ran so deep that scientists acted on it. They did not just calculate the probability of alien civilizations, they tried to reach them. In 1972, NASA launched Pioneer 10 toward Jupiter. Bolted to its frame was a gold anodized aluminum plaque engraved with information about its origin, a drawing of a man and a woman, a diagram of the hydrogen atom, a map showing the position of our sun relative to 14 pulsars in the galaxy, each one labelled with its precise period. A cosmic address that any civilization capable of reading it could use to locate us. Pioneer 10 was never expected to be intercepted. It was a message in a bottle thrown into the deepest ocean imaginable, a gesture built on the assumption that somewhere out there, someone might one day pick it up. 5 years later, in 1977, NASA went further. Voyager 1 and Voyager 2 each carried a golden record, a 12-inch gold-plated copper disc containing 115 images, greetings in 55 languages, a 90-minute selection of music from cultures around the world, and a collection of natural sounds including wind, thunder, birdsong, and a human heartbeat. The cover of the record included instructions for playing it, encoded in the universal language of physics, along with the same pulsar map used on Pioneer 10. Carl Sagan, who chaired the committee that assembled the record, described it as something of a cosmic message in a bottle, but the intent was serious. It was an artifact designed to survive in interstellar space for hundreds of millions of years, waiting to be found. Then, in 1974, astronomers used the Arecibo radio telescope in Puerto Rico to transmit a carefully constructed message toward a star cluster called M13, roughly 22,000 light-years away. The message was composed of 1,679 binary digits, arranged to encode information about human DNA, the solar system, and the Arecibo dish itself. It was the most powerful, deliberate broadcast ever aimed at the stars. It will arrive at its destination in approximately 22,000 years. If anyone there sends a reply, it will arrive back here in another 22,000 years. A single round-trip conversation spanning 44,000 years. These were not the acts of fringe enthusiasts. They were conducted by NASA, by national observatories, by committees that included some of the most respected scientists in the world. The assumption behind all of them was the same. Contact is possible. The universe is a space where messages can be sent and received, where artifacts can be found, where the act of reaching out has a non-zero chance of producing an answer. That assumption felt so natural, so self-evident that almost no one questioned it. Of course, you send a message. Of course, you include a return address. Of course, someone might find it. The alternative, that the message might travel for millions of years without ever encountering a mind capable of reading it, was not seriously considered. The expectation of contact was not a hypothesis. It was an axiom, a starting point so deeply embedded in the scientific culture that it shaped the design of spacecraft and the allocation of national budgets. And it was built on a foundation that, as we are about to see, does not hold. In the decades since, some of those unknowns have been filled in. The Kepler mission and its successor, the Transiting Exoplanet Survey satellite, resolved the planet question decisively. That variable in the Drake equation, the fraction of stars with planets, turned out to be close to 1, just as we described moments ago. What has not been resolved is everything that comes after. The raw ingredients for life, water, carbon compounds, energy sources, have been found scattered across the galaxy in quantities that would have astonished Drake's original group. but other variables remain stubbornly uncertain. How often does chemistry become biology? We still do not know. How often does biology produce intelligence? We have one example and no way to determine whether it was inevitable or a freak accident. How long does a technological civilization survive once it splits the atom and builds broadcast towers? We have no data at all. Those unknowns are the cracks in the foundation. Small changes in any one of them can flood the entire calculation or drain it dry. Push a few of them low enough and the galaxy goes from a crowded city to a graveyard. Push them higher and we should have neighbors on every block. But there is something deeper going on here. Something the Drake equation does not capture, and that most discussions of the Fermi paradox glide past too quickly. The equation asks how many civilizations exist. It does not ask whether any of them can reach each other. And that distinction is the crack that splits the entire problem wide open. Think about what the question, "Where is everybody?" actually assumes. It assumes that if intelligent civilizations exist, they should eventually become detectable to us, either through signals they deliberately send, or through signals they accidentally leak, or through physical evidence of their engineering, or through direct visitation. The assumption is that existence leads to visibility, that if you are out there long enough and smart enough, eventually someone notices. This assumption feels natural. In our daily experience on Earth, things that exist can be found. Civilizations that build things leave traces. The intuition is that existence and reachability are connected. That if you are real, you are findable. Science fiction reinforced this intuition for over a century. In nearly every story, every film, every television series involving alien life, contact happens. Sometimes it is peaceful, sometimes it is violent, sometimes it takes decades, sometimes it takes minutes, but it happens. Starships cross the galaxy in hours. Radio signals reach alien ears and are understood. Species meet, negotiate, fight, trade, cooperate. The narrative demands it. A story about aliens you never meet is a story with no plot. But fiction does not obey physics. Fiction can ignore the speed of light whenever the story requires it. Fiction can compress distances that would take tens of thousands of years to cross into a scene transition lasting 3 seconds. Fiction can place two civilizations in adjacent star systems and have them exchange ambassadors within a week. The audience never questions it because the story depends on it. Reality operates under a different set of rules, and those rules do not care about the story. Here is where the expectation begins to fracture. The assumption that existence leads to contact depends on several conditions all being true at the same time. The civilizations must exist at the same moment in cosmic history. They must be close enough for signals or travel to bridge the gap. The signals must remain strong enough over that distance to be detectable. The travel, if attempted, must be physically possible within the lifespan of the civilization attempting it. And both civilizations must survive long enough to complete the exchange. Each of those conditions sounds achievable on its own. Each one, taken in isolation, seems like a problem that a sufficiently advanced species could solve. But they are not independent problems. They are layered. They compound. They multiply against each other in ways that transform a series of difficult challenges into a barrier that may be structurally insurmountable. Let us begin with the most basic layer. The numbers that make the universe feel so full of potential are the same numbers that make it feel impossibly vast. The Milky Way is roughly 100,000 light years across. That means light itself, The fastest thing permitted by the laws of physics takes 100,000 years to travel from one side of our galaxy to the other. A radio signal broadcast from a civilization on the far side of the Milky Way right now, at this exact moment, would not arrive here for 100,000 years. And that is within our own galaxy. The nearest large galaxy, Andromeda, is approximately 2.5 million light years away. The observable universe stretches roughly 93 billion light years from edge to edge, and most of it is already receding from us faster than light can cross the gap, carried away by the expansion of space itself. These are not just large distances. They are distances that redefine what far away means. On Earth, distance is an inconvenience. You drive longer, you fly farther, you wait a few more hours. In space, distance is a wall. A wall made not of matter, but of time. The distance between stars is measured in the years it takes light to cross it. And light is already traveling at the absolute maximum speed the universe allows. Consider the nearest star to our own. Proxima Centauri sits approximately 4.2 light years from Earth. In everyday terms, that is roughly 40 trillion kilometers. If you could somehow drive a car at highway speed without stopping, the trip would take roughly 50 million years. The fastest human-made object leaving the solar system, Voyager 1, travels at roughly 17 kilometers per second. At that speed, reaching Proxima Centauri would take over 70,000 years. And Proxima Centauri is the closest star, the nearest one, the easy one. Most of the stars in the Milky Way are thousands of light years away. Many are tens of thousands. The center of the galaxy is roughly 26,000 light years from Earth. A signal sent from here to the galactic core, traveling at the speed of light, would arrive in 26,000 years. A reply, if one came instantly, would take another 26,000 years to reach us. A single exchange would span 52,000 years. That is longer than the entire history of human civilization. Longer than agriculture, longer than written language, longer than every empire, every war, every book, every idea humanity has ever produced. That is the distance to the center of our own galaxy, not to another galaxy, not to the edge of the observable universe, just to the middle of the one we live in. Most people, when they hear numbers like these, experience a brief flicker of awe and then move on. The scale is so far beyond daily experience that the mind slides off it. But the implications of these distances are not abstract. They are structural. They define what is possible and what is not. And they begin to explain why the expectation of contact is built on a foundation that may not hold. Here is the part that rarely gets discussed with the precision it deserves. The expectation of contact assumes that distance is a problem of engineering. That with enough time, enough technology, enough determination, a civilization can bridge any gap. Science fiction trained us to think this way. We imagine faster engines, better fuels, generation ships, wormholes, warp drives. We treat distance as a challenge that ingenuity can overcome, the way our ancestors overcame oceans and mountains and deserts. But the distance between stars is not an ocean. It is not a desert. It is not a challenge of the same category. The distance between stars is a consequence of the fundamental structure of spacetime. The speed of light is not a speed limit, in the way that a highway speed limit is a speed limit. It is not a rule imposed by an authority that a sufficiently clever traveler could circumvent. It is a property of the universe itself. It is the speed at which causality propagates. It is the maximum rate at which information, matter, energy, or influence of any kind can move through space, and it cannot be exceeded by any known mechanism consistent with the laws of physics as we understand them. This is not a technological limitation, it is a structural one. It does not matter how advanced a civilization becomes, it does not matter how much energy they command, it does not matter how many millennia they have been trying. The speed of light is woven into the geometry of space-time at the deepest level physics has ever reached. Every experiment ever conducted, every observation ever made, every theoretical framework that has survived experimental testing confirms it. Nothing travels faster, and that single fact transforms the question of alien contact from a problem of will and capability into a problem of architecture. We imagine the cosmos as a connected space, a place where sufficiently loud voices could be heard by sufficiently sensitive ears. The reality is something else entirely. The gaps between stars are measured in years, and the stars themselves are moving apart. The Drake equation counts civilizations. It does not measure the space between them. It does not account for the time a signal takes to cross that space. It does not factor in whether the signal is still detectable when it arrives, whether the receiving civilization still exists, whether they happen to be listening on the right frequency at the right moment, or whether the sender survived long enough to hear a reply. When you add those factors, the equation changes, not gradually, not by small adjustments. The probability of contact does not decline. It collapses. It falls through the floor, not because life is rare, but because the universe is built on a scale and at a speed that makes connection between distant points extraordinarily, perhaps permanently, difficult. This is the fracture in the expectation. The numbers that make the universe feel alive with possibility are the same numbers that make contact feel impossible. 2 trillion galaxies is not just a statement about abundance, it is a statement about separation. Billions of habitable worlds is not just a promise of life, it is a description of how far apart those lives would be. The universe did not scatter the ingredients for life across a cozy neighborhood. It scattered them across a void so vast that light, the fastest messenger reality allows, takes billions of years to cross it. And here is what most discussions of the Fermi paradox miss entirely. The paradox is usually framed as a question about whether aliens exist. Are they out there? Why have we not heard from them? What is stopping them? But those are the wrong questions. The existence of alien life is a question of biology, of chemistry, of probability. It is a question that may have a reassuring answer. Life may be common. Intelligence may arise frequently. Civilizations may bloom across the galaxy in numbers that would fill Drake's equation to overflowing. The real question is not whether they exist. The real question is whether the universe allows them to reach each other. Whether the structure of space-time, the speed of light, the distances between stars, the expansion of space, and the finite lifespans of civilizations create a cosmos where contact is possible, or whether they create one where contact is forbidden by architecture. That question has a very different character. It is not a question about biology. It is a question about physics. And physics does not negotiate. The expectation of contact was built on abundance. The universe has the stars. It has the planets. It has the chemistry. It has the time. Surely with all of that, someone somewhere should have reached someone else by now. But abundance and accessibility are not the same thing. A library with 1 billion books is useless if every book is locked in a separate vault on a separate continent, and the roads between them take 1,000 years to travel. The books exist. The knowledge is real, but no single reader will ever hold more than one. The universe may be that library, and the vaults may be locked not by intention, not by malice, not by conspiracy, but by the geometry of the shelves themselves. Everything that follows in this story is about those locks, about the walls between the vaults, about why they are there, how thick they are, and whether anything, any technology, any determination, any amount of time can ever open them. The first lock is distance, and distance, as you are about to discover, is far more brutal than the word suggests. It is not a gap to be crossed. It is a cage built into the fabric of everything that exists. And the bars are made of light years. We established that the nearest star to our sun, Proxima Centauri, sits approximately 4.2 light years from Earth. We noted the distances. We introduced the speed of light as the universe's absolute maximum. But we did not yet explain what that limit actually means for anything trying to move through space, or for anything trying to send a message across it. This is where the expectation of contact does not just weaken, it breaks. Let us start with what the speed of light actually is, not in the poetic sense, in the mechanical, structural, no room for negotiation sense. Light travels at approximately 300,000 kilometers per second. In 1 second, a beam of light could circle the Earth more than 7 times. In 1 year, it covers roughly 9.5 trillion kilometers. That distance, 1 light year, is the ruler scientists use to measure the gaps between stars. And even that ruler, built from the fastest speed reality permits, produces numbers that are staggering. 4.2 light years to the nearest star means that a beam of light departing Earth right now would arrive at Proxima Centauri roughly 4 years and 2 months from today. That is the fastest anything can make the trip. Not the fastest we have built, the fastest anything can ever go. If a civilization 1 billion years more advanced than ours pointed every joule of energy they possessed at crossing that gap, they could not beat a flashlight by a single second. The speed of light is not a record to be broken. It is a boundary condition of the universe as fundamental as the existence of matter itself. Einstein showed why in 1905. His theory of special relativity demonstrates that as any object with mass accelerates toward the speed of light, the energy required to push it faster increases without limit. To accelerate a single kilogram of matter to exactly the speed of light would require infinite energy. Not a lot of energy. Literally infinite. A quantity that does not exist in the physical universe. This is confirmed by every particle accelerator ever built. At CERN, physicists routinely accelerate subatomic particles to 99.9999% of the speed of light. The energy required to push them that last vanishing fraction closer is greater than the energy used for all the preceding acceleration combined. And they still never reach it. So nothing with mass ever travels at the speed of light. The best any civilization could ever achieve, no matter how advanced, is some fraction of it. And this is where the engineering reality becomes devastating. In 1903, a Russian scientist named Konstantin Tsiolkovsky published what became known as the rocket equation. It describes the relationship between a spacecraft's final speed, the speed of its exhaust, and the ratio of its total mass, including fuel to its empty mass without fuel. The equation is simple. Its consequences are brutal. A rocket must carry its own fuel. That fuel has mass. The rocket must also accelerate the fuel it has not yet burned, which means it needs more fuel to carry the fuel. The requirement grows exponentially. For every additional increment of speed, the amount of fuel needed does not just grow, it multiplies. With chemical rockets, the kind that launched every spacecraft humanity has ever built, the fuel required to send a single human being to the nearest star within a human lifetime would exceed the mass of the observable universe. That is not an exaggeration. It is a direct calculation from the rocket equation using the exhaust velocities of chemical propulsion. The number is so absurdly large that it disqualifies the approach entirely. More advanced propulsion concepts exist on paper. Nuclear pulse propulsion, where a spacecraft detonates nuclear bombs behind it and rides the shockwave. Nuclear fusion drives, antimatter engines, light sails pushed by massive ground-based laser arrays. Each of these improves the exhaust velocity and therefore reduces the fuel ratio. But none of them eliminate the fundamental problem. They merely move the numbers from the realm of the impossible into the realm of the extraordinarily difficult. Take the most optimistic near-term proposal currently under serious scientific discussion. Breakthrough Starshot, funded by investor Yuri Milner and publicly championed by the late physicist Stephen Hawking, proposes to send a fleet of tiny spacecraft, each weighing only a few grams, to the Alpha Centauri system using a ground-based laser array that would accelerate them to roughly 20% of the speed of light. At that speed, the journey would take approximately 20 years. The probes would fly through the system in a matter of hours, snap images, and beam data back to Earth using onboard lasers. The return signal, traveling at the speed of light, would arrive roughly 4 years later. That is the most ambitious interstellar travel proposal humanity has ever seriously considered. And what does it deliver? A few grams of electronics, no larger than a postage stamp, flung past a neighboring star at 1/5 of light speed, with no ability to slow down, orbit, or land. A snapshot taken from a bullet, sending anything larger, anything with enough mass to carry instruments, communication equipment, power systems, or passengers, changes the equation drastically. The laser array required to push even a small payload to 20% of light speed would need to be kilometers across and consume more power than most nations generate. Scaling that up to a crewed vessel is not a matter of building a bigger laser. It is a matter of confronting the exponential wall of the rocket equation at every stage, a wall that grows faster than any technology in human history has ever climbed. And even if a civilization solved the propulsion problem, even if they found a way to push a meaningful payload to 10 or 20% of light speed, the journey to any star beyond the immediate solar neighborhood would still take decades, centuries, or millennia. At 10% of light speed, crossing the Milky Way from edge to edge would take 1 million years. 1 million years of continuous flight, with no stops, no maintenance, no resupply, through a medium that is not truly empty, but filled with dust grains, hydrogen atoms, and cosmic radiation that would slowly erode any physical structure. That medium deserves closer examination, because interstellar space is not the clean vacuum that the word suggests. It is thin, extraordinarily thin by any terrestrial standard, but it is not empty. And at relativistic speeds, the difference between thin and empty becomes the difference between survival and destruction. The interstellar medium contains roughly 1 atom per cubic centimeter on average. At rest, that density is negligible. At 10% of the speed of light, roughly 30,000 kilometers per second, every one of those atoms becomes a source of damage. No single hydrogen atom at that speed delivers dramatic energy. Each impact releases less than a trillionth of a joule, but a spacecraft traveling at 10% of light speed sweeps through billions of these atoms every second across every square meter of its forward-facing surface. The cumulative effect is a relentless bombardment, equivalent to a steady stream of ionizing radiation, slowly degrading hull materials, eroding surface layers, and damaging electronic systems over the years and decades of transit. The dose increases with the square of the velocity, and no amount of speed makes the medium safer. Faster always means more punishment. At higher fractions of light speed, the problem escalates from erosion to destruction. A grain of interstellar dust 1 micrometer across, weighing less than a trillionth of a gram, striking a spacecraft at 50% of light speed releases roughly 20 joules of energy, comparable to the impact of a pellet from an air rifle. That sounds trivial until you remember that a vessel traveling through even moderately dusty regions of the galaxy encounters thousands of such impacts per second across its forward surface. The cumulative effect is a sandblaster operating at relativistic speed. A grain of sand, perhaps half a millimeter across, at the same speed releases energy equivalent to roughly half a ton of TNT. A single grain, one impact, at a velocity that any interstellar mission with meaningful speed would need to approach. These are not collisions that shielding can absorb passively. They are impacts that would puncture, vaporize, or structurally compromise any material known to engineering. And the dust is not avoidable. The galaxy is threaded with it. Denser clouds of interstellar dust concentrate along the spiral arms and within the plane of the galactic disk, precisely the regions through which any interstellar voyage would need to pass. A ship traveling at relativistic speed cannot steer around individual grains. It encounters billions of them per second across its forward cross-section. The only defense is either a physical shield massive enough to absorb the bombardment, which adds enormous mass and circles back to the fuel problem, or a magnetic deflection system powerful enough to sweep charged particles out of the flight path, which works for ions but not for neutral dust grains. Then there is radiation. At rest, a spacecraft in interstellar space is exposed to a baseline level of cosmic radiation. High-energy particles from distant supernovae, active galactic nuclei, and other energetic sources across the galaxy. This background radiation is manageable with modest shielding. But a spacecraft moving at relativistic speed does not experience background radiation the same way a stationary object does. The phenomenon called relativistic aberration compresses the incoming radiation field into a concentrated beam focused directly ahead of the vessel. From the ship's frame of reference, the universe in front of it appears to blue shift, with incoming photons gaining energy proportional to the velocity. At a significant fraction of light speed, ordinary starlight ahead of the vessel shifts into the ultraviolet, then into the X-ray range, then into the gamma-ray range. The forward sky becomes a searchlight of lethal radiation that intensifies the faster the ship moves. Shielding against gamma radiation requires meters of dense material, lead or concrete on Earth, which adds mass that the propulsion system must accelerate along with everything else. The paradox is vicious. The faster you go, the more radiation you face. The more shielding you carry, the more fuel you need. The more fuel you carry, the harder it is to reach the speed that created the problem in the first place. Every proposed interstellar propulsion concept has to contend with these realities. They are not engineering inconveniences that a sufficiently clever design can work around. They are physical consequences of moving through a medium at velocities that transform ordinary matter into ammunition and ordinary light into a weapon. The interstellar medium is not a highway. It is a gauntlet. At this point, a reasonable objection arises. What about shortcuts? What about wormholes? What about warp drives? What about the theoretical loopholes in general relativity that science fiction has used for decades to bypass the speed of light entirely? The objection deserves a direct answer because these concepts are not pure fantasy. They are grounded in real physics, published in peer-reviewed journals, discussed seriously by credentialed researchers. But the gap between what the mathematics permits in theory and what the universe permits in practice is enormous. And in every case, the gap has widened as scientists have looked more closely. Wormholes, sometimes called Einstein-Rosen bridges, are solutions to the equations of general relativity that describe a tunnel connecting two distant points in spacetime. They were first proposed mathematically in 1935. In principle, entering one end of a wormhole and exiting the other would allow a traveler to bypass the intervening space entirely, arriving at a destination light years away without traversing the distance between. The problem is that every known solution for a traversable wormhole, one that a physical object could actually pass through without being destroyed, requires a substance called exotic matter. Exotic matter is not merely rare or expensive, it is a hypothetical form of matter with negative energy density, a property that no known material possesses and that may not be physically possible. Negative energy density means the substance would gravitationally repel rather than attract, a behavior opposite to every form of matter and energy ever observed or created in any laboratory on Earth. Without it, the throat of the wormhole collapses faster than anything can pass through. The bridge exists on paper. In reality, it slams shut. Some researchers have explored whether quantum effects could produce the tiny amounts of negative energy needed to stabilize a microscopic wormhole. The Casimir effect, a real and measured quantum phenomenon, does produce regions of negative energy density under very specific conditions. But the quantities involved are fantastically small, trillions of times too weak to stabilize a wormhole large enough for even a single photon to pass through, let alone a spacecraft or a signal. Warp drives face similar problems. In 1994, physicist Miguel Alcubierre published a paper describing a solution to Einstein's field equations in which a bubble of warped spacetime could carry a spacecraft at effectively faster than light speeds without violating local relativity. Inside the bubble, the ship is stationary. The space behind it expands. The space ahead of it contracts. The ship surfs a wave of space-time distortion, arriving at its destination faster than light could travel through normal space. The mathematics works. The energy requirements do not. Alcubierre's original calculation suggested that creating such a bubble would require negative energy roughly equivalent to the mass energy of the entire observable universe. Subsequent refinements by other researchers reduced that estimate dramatically, with some configurations bringing the requirement down to roughly the mass energy of Jupiter. But even those most optimistic versions still require exotic matter in quantities that have never been observed anywhere in the universe. And the negative energy must be arranged in a precise geometric configuration around the vessel. A shell of exotic matter with tolerances that no known manufacturing process could achieve. There are additional problems that go beyond energy. Several analyses have shown that the interior of an Alcubierre bubble would accumulate high-energy particles during transit, releasing them in a catastrophic burst upon deceleration, a burst energetic enough to sterilize the destination. Others have demonstrated that a warp bubble, once created, could not be steered or stopped from within, because the occupants are causally disconnected from the bubble wall. And the most fundamental objection is that any mechanism allowing faster than light travel also permits violations of causality, the creation of closed time-like curves that would allow effects to precede their causes. Most physicists regard this as a strong indicator that nature prohibits the mechanism entirely, even if the equations technically permit it. The honest summary is this: general relativity contains mathematical solutions that describe faster than light travel and shortcuts through space-time. But every one of those solutions requires physical conditions that have never been observed, materials that may not exist, and energy levels that exceed anything available in the known universe. They are theorems about what the equations allow, not descriptions of what reality provides. And until exotic matter is discovered, until negative energy density is produced at macroscopic scales, until causality violations are shown to be physically permissible, they remain exactly what they have been since they were first proposed: mathematics without a machine. The speed of light is not a puzzle waiting for a clever solution. It is a constraint so deeply embedded in the logic of cause and effect that removing it does not just change the rules of travel, it unravels the coherence of time itself. Working around it is not an engineering problem. It may be a logical impossibility. The travelers who departed would never arrive. Their descendants might, if the vessel survived, if the biology survived, if the social structure survived, if the purpose survived. 1,000,000 years is longer than our species has existed. This is the reality of interstellar travel, even at a fraction of light speed, even with propulsion systems that do not yet exist. The distances are so vast, and the speed limits so firm, that crossing them requires not just advanced technology, but a commitment measured in geological time. And geological time is not a resource that civilizations have been shown to possess. But travel is only half the contact problem. Perhaps civilizations do not need to visit each other. Perhaps they only need to communicate. Perhaps a radio signal, a laser pulse, a message carried on electromagnetic waves at the speed of light is enough to bridge the gap. This is the hope that drives the search for extraterrestrial intelligence. Forget ships. Forget passengers. Just listen. If a civilization anywhere in the galaxy has ever broadcast a signal strong enough and aimed in our direction, we should be able to detect it. The electromagnetic spectrum is the most efficient messenger in the universe. It travels at the maximum speed. It requires no fuel. It costs only the energy of transmission. Surely, across billions of years and trillions of worlds, someone somewhere has said something. The physics of electromagnetic communication across interstellar distances is not generous. A radio signal, like all electromagnetic radiation, weakens according to the inverse square law. This means that when you double the distance from the source, the signal does not become half as strong, it becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. At 10 times the distance, it is 1/100th as strong. The signal spreads outward in an expanding sphere, and the energy is distributed across the growing surface of that sphere. The farther it travels, the thinner it gets. Earth has been broadcasting radio signals for roughly a century. Those signals have traveled outward in a sphere that now extends roughly 100 light years in every direction. That sounds impressive until you remember that the Milky Way is 100,000 light years across. Our radio bubble covers a volume of space containing roughly 15,000 stars. The galaxy contains hundreds of billions. Our century of broadcasting has reached less than 100,000th of the galaxy. And here is the part that most discussions leave out. Those signals were not designed for interstellar communication. They were television broadcasts, military radar, FM radio, cell towers. Their power levels were calibrated for receivers on the same planet, not for receivers around other stars. By the time our strongest Cold War era radar signals reach even the nearest stars, they have weakened to the point where detecting them would require an antenna larger than anything humanity has ever built. At a distance of a few hundred light years, they are indistinguishable from the natural background noise of the cosmos. They are gone, swallowed by the static of the universe, and the static is not a figure of speech. The galaxy is loud, not in the acoustic sense, but in the electromagnetic sense. The radio spectrum that we use to search for alien signals is filled with natural emissions from every category of energetic object the universe produces. Pulsars broadcast regular pulses of radio energy across the galaxy. Magnetars produce sporadic bursts that can briefly outshine entire solar systems in the radio band. The supermassive black hole at the center of the Milky Way, Sagittarius IY star, emits radio waves as matter spirals into its accretion disk. Supernova remnants radiate across a wide range of frequencies. Even the cosmic microwave background contributes a baseline hum that pervades the entire observable universe. Any artificial signal crossing interstellar space must compete against this noise. And the competition is not fair. A natural source like a pulsar can radiate millions of times more power than any transmitter a civilization could reasonably build. An artificial signal, weakened by the inverse square law over thousands of light years, arrives as a faint whisper against a background of cosmic shouting. There are also effects that degrade the signal itself during transit. The interstellar medium is not uniform. It contains pockets of ionized hydrogen, regions of turbulent plasma, and density variations that affect radio waves passing through them. One consequence is interstellar scintillation, a process analogous to the twinkling of stars caused by Earth's atmosphere. As a radio signal passes through turbulent plasma between stars, its intensity fluctuates randomly. A steady transmission becomes a flickering one. A signal that was strong at the source might fade to undetectable levels at the receiver for minutes or hours at a time, then briefly reappear before fading again. Detecting such a signal requires sustained observation of the same patch of sky over extended periods. Exactly the kind of patient, targeted listening that is most expensive in telescope time and most difficult to fund. Another consequence is dispersion. Different frequencies travel through ionized plasma at slightly different speeds. A broadband signal that leaves its source as a sharp pulse arrives at the receiver smeared out in time, with higher frequencies arriving before lower ones. The amount of smearing depends on the total column of free electrons between the source and the receiver, a quantity that varies with direction and distance and is not precisely known for most lines of sight through the galaxy. Correcting for dispersion is possible, but it requires guessing the amount of smearing and testing each guess individually, multiplying the computational cost of the search enormously. The combination of noise, scintillation, and dispersion means that the galaxy is not a quiet auditorium where a single clear voice could be heard across the hall. It is closer to a crowded stadium during a thunderstorm, where a single person speaking at normal volume from the far end of the field has no realistic chance of being heard by anyone in the stands, no matter how carefully they listen. A civilization that wanted to be heard across interstellar distances would need to do something deliberate. They would need to build a dedicated transmitter, aim it at a specific target, and pour enormous energy into a tightly focused beam. Even then, the inverse square law imposes harsh limits. A signal sent from the far side of the galaxy, 26,000 light-years away, even using a transmitter powered by the energy output of an entire star, would arrive as a whisper buried under the roar of cosmic background radiation. Detection is not just a matter of having a big enough antenna. It is a matter of knowing where to point it, what frequency to listen on, and when to listen. A tightly beamed signal aimed at a specific star is efficient, but it only reaches one target. A signal broadcast in all directions reaches everyone, but it is diluted across the entire sky. There is a fundamental trade-off between reach and strength, and the universe does not offer a way around it. Consider what a successful interstellar conversation would actually require. Civilization A broadcasts a message. The signal travels at the speed of light to Civilization B. If Civilization B is 1,000 light-years away, the signal takes 1,000 years to arrive. Civilization B detects it, decodes it, and sends a reply. The reply takes another 1,000 years to return. A single exchange, one question and one answer, spans 2,000 years. 2,000 years ago, the Roman Empire was at its height. Everything about human civilization has changed beyond recognition since then. That is the span of time required to complete one round-trip conversation with a civilization 1,000 light-years away. And 1,000 light-years is roughly 1% of the Milky Way's diameter. For a civilization 10,000 light-years away, one round-trip exchange takes 20,000 years. For one on the far side of the galaxy, it takes roughly 50,000 years. No civilization in the history of Earth has maintained continuous institutional memory for even 5,000 years. The idea of sustaining a conversation that unfolds over 50,000 years assumes a level of cultural continuity and patience that no known species has ever demonstrated. And that is within our own galaxy. Step outside the Milky Way and the numbers become truly terrifying. The Andromeda Galaxy, the nearest large galaxy, is approximately 2.5 million light-years away. A round-trip exchange would span 5 million years. An entire evolutionary epoch fits inside a single conversation with our nearest galactic neighbor. Beyond Andromeda, the distances escalate into the billions of light-years, and here, a new barrier emerges that is even more absolute than the speed of light itself. The universe is expanding, not in the way a balloon expands in a room, pushing outward into existing space. Space itself is stretching. The distance between galaxies that are not gravitationally bound to each other is increasing, not because they are moving through space, but because the space between them is growing. This expansion has a rate measured by the Hubble constant. At relatively small scales, within our local group of galaxies, the expansion is negligible. Gravity holds nearby galaxies together. But at greater distances, the expansion becomes significant. And at a sufficient distance, the expansion of space exceeds the speed of light. At roughly 14 billion light-years, known as the Hubble radius, The recession velocity equals light speed. But the true boundary of permanent unreachability sits even further out, at what physicists call the cosmic event horizon. Approximately 16 to 17 billion light years away in comoving distance. Beyond that threshold, any light emitted now, any signal sent now, will never reach us, no matter how long we wait. The photon sets out in our direction, but the space it must cross stretches faster than it can travel, and the gap between us grows with every passing moment. These galaxies are permanently unreachable, not because of any technological limitation, but because the fabric of space-time itself is carrying them beyond the point of no return. And the expansion is accelerating, driven by what physicists call dark energy, a phenomenon that constitutes roughly 68% of the total energy content of the universe and remains almost entirely unexplained. The rate at which distant galaxies recede from us is increasing over time. This means the cosmic horizon is not static. It is shrinking. The volume of the universe that is even theoretically reachable is getting smaller with every passing moment. Galaxies that are visible today will eventually cross the horizon and disappear from the observable universe forever. Given enough time, every galaxy beyond our local group will have receded beyond the point of no return. The Milky Way and its nearest neighbors will be an island in an otherwise empty void, surrounded by a darkness from which no signal, no light, no information of any kind can ever emerge. This is not a distant future measured in trillions of years, though the full effect unfolds on that scale. The process is happening now, right now, as you listen to this. The observable universe is losing galaxies across the horizon. Objects that were once within reach are being carried away by the expansion of space. The reachable universe is contracting. For any civilization anywhere in the cosmos, this means the same thing. The pool of potential contacts is not growing. It is shrinking. Every year, every century, every millennium, the number of civilizations that could ever theoretically be reached, even by a signal traveling at the maximum speed the universe allows, gets smaller. The window is closing. And it was never very wide to begin with. Let us bring this back from the cosmic scale to the immediate one. Forget other galaxies. Forget the cosmic horizon. Forget the expansion of space. Consider only our own galaxy, the Milky Way. 100,000 light years across. 200 billion to 400 billion stars. Billions of potentially habitable planets. Even here, within our own galactic home, the barriers are immense. A civilization on the other side of the Milky Way, transmitting a signal directly at us using a transmitter of extraordinary power, would produce a signal that takes 100,000 years to arrive. If we detected it and replied, the round trip would take 200,000 years. No human institution has ever lasted that long. No human language has survived unchanged for even 10,000 years. The civilization that sent the message might not exist by the time our reply arrives. The civilization that sent the reply might not exist by the time we receive it. And this assumes perfect conditions. It assumes the signal survives the journey without being scattered, absorbed, or drowned in noise. It assumes both civilizations happen to be listening on the same frequency at the same time. It assumes neither civilization is destroyed by natural disaster, internal collapse, or cosmic accident during the transit window. Every one of those assumptions is optimistic. Every one of them could fail. And if even one fails, the conversation never happens. This is what distance does to contact. It does not merely make it hard, it transforms contact from a problem of engineering into a problem of endurance, coordination, and luck, operating on timescales that dwarf every structure civilization has ever built. The speed of light does not connect the universe, it isolates it. It creates a cosmos where the maximum speed of information transfer is far too slow to bridge the gaps between the places where information might originate. The expectation of contact was built on a picture of the universe as a connected space, a room where sufficiently loud voices could be heard by sufficiently sensitive ears. The reality is close to the opposite. The universe is a collection of isolated rooms, separated by corridors so long that walking them takes longer than the rooms themselves survive. By the time anyone reaches the next door, the occupants are gone. And none of this accounts for the harshest variable of all. Everything we have discussed so far assumes that civilizations last long enough to participate in the exchange, that they survive, that they endure, that they maintain their technology, their curiosity, their coherence, and their will across the millennia required for even the simplest form of contact. That assumption is the subject of what comes next. Because the universe does not just separate civilizations by distance, it separates them by time. And time, it turns out, is an even crueler barrier than space. The speed of light built the walls, the expansion of space locked the doors. But the clock that governs how long any civilization gets to try those doors is ticking on a scale that makes the odds of overlapping with anyone else almost vanishingly small. The wall of distance is brutal. The wall of time may be worse. Distance built the walls. The speed of light sealed them. But even if some extraordinary civilization found a way to push a signal or a ship across the void between stars, there is another barrier waiting, one that does not depend on engineering or physics, but on something far more fragile. Time. Not time in the abstract. Not the poetic sense of time passing. Time in the brutally specific sense of whether two civilizations happen to exist during the same window, in the same part of the galaxy, with the same capacity to send and receive, at the same moment in a story that has been running for 13 billion years. We established earlier that the galaxy has existed for approximately 13 billion years. But that number meant something different in the context of distance. Here, it means something worse. 13 billion years is not just a measure of how far away things are. It is a measure of how many chances the galaxy has had to produce civilizations, and how thinly those chances are spread across time. Planets have existed for nearly as long as the galaxy itself. The raw chemistry of life, carbon, hydrogen, oxygen, nitrogen, has been scattered through interstellar space by dying stars for billions of years. If life can emerge from that chemistry, it has had an enormous window in which to do so. Not millions of years, billions. Now consider the other side of the equation. Humanity has possessed the ability to send or detect interstellar signals for roughly 100 years. That is the window. 100 years out of 13 billion. To feel the weight of that ratio, imagine the entire history of the Milky Way compressed into a single calendar year. January 1st is the formation of the galaxy. December 31st at midnight is right now. On that calendar, all of recorded human history, every empire, every war, every scientific revolution, everything from the invention of writing to the launch of the James Webb Space Telescope, fits into roughly the last 12 seconds before midnight, on December 31st. Our technological window, the period during which we have been capable of participating in interstellar communication, does not even register as a visible mark on that timeline. It is a sliver so thin that if you printed the entire calendar year on a wall, the length of a football field, our window would be smaller than a single bacterium, roughly the width of a single wavelength of light, permanently invisible no matter how closely you looked. That is not a metaphor chosen for drama. It is a mathematical description of the ratio. 100 years divided by 13 billion years. The result is a number so small that it functionally rounds to zero. Now consider what this means for contact. For two civilizations to communicate, they must both be active at the same time. They must both possess the technology to send and receive signals during the same overlapping window. If Civilization A existed 3 billion years ago and lasted for 1 million years, and Civilization B exists now and will last for 10,000 years, they will never know about each other. Their windows do not touch. They are separated not by distance alone, but by time. And time is a dimension that no signal, no ship, and no technology can reverse. This is called the synchronicity problem, and it is one of the most underappreciated barriers to contact in the entire Fermi paradox. The galaxy may have produced thousands of civilizations across its history, perhaps tens of thousands, perhaps more. But if each one lasted for only a brief moment by cosmic standards, a few thousand years, a few tens of thousands, then the probability that any two of them overlapped in time is shockingly low. A study published in 2025 by Manuel Schorf and Helmut Lahmor of the Austrian Academy of Sciences addressed this directly. Their work modeled the emergence and duration of technological civilizations across the Milky Way, factoring in the distribution of habitable planets, the time required for intelligent life to evolve, and the expected lifespan of technological species. Their conclusion was striking. For even one other technological civilization to exist in the galaxy at the same time as ours, that civilization would need to persist for at least 280,000 years. For 10 civilizations to coexist simultaneously, the average lifespan would need to exceed 10 million years. 280,000 years. Humanity in its modern anatomical form has existed for roughly 300,000 years. But we have possessed technology capable of interstellar communication for only about 100 of those years. The gap between biological existence and technological capability is enormous. A species can exist for hundreds of thousands of years without ever building a radio transmitter. And the window of technological communication might be far shorter than the window of biological survival. A separate study published in 2026 in the monthly notices of the Royal Astronomical Society reinforced this conclusion from a different angle. The researchers argued that if intelligent life is common in the galaxy, the absence of any detected signal constrains the average lifespan of technological civilizations to less than roughly 5,000 years under optimistic assumptions. 5,000 years. That is approximately the span from the earliest Mesopotamian city-states to the present day. One full arc of complex human civilization. And the math says that if civilizations typically last about that long, the galaxy could produce many of them sequentially without any two ever overlapping in time or proximity enough to detect each other. Think about what that means. The galaxy could be a place where civilizations bloom and die like flowers in a field, each one opening for a brief season and then fading, each one surrounded by empty ground where other flowers once stood or will stand in the future. At any given moment, the field might contain only one flower, or two, or none. The soil is fertile. The seeds are everywhere. But the growing season for each individual bloom is so short relative to the age of the field that the flowers almost never see each other. This is not an exotic theoretical scenario. It is what the numbers predict when you combine the likely frequency of civilizations with the likely duration of their technological windows. The galaxy does not need to be empty to be silent. It only needs to be poorly synchronized. And synchronization gets worse when you factor distance back in. Even if two civilizations do happen to exist at the same time, they must also be close enough for signals to bridge the gap within their shared window. If Civilization A and Civilization B are both active for 10,000 years, but they are separated by 50,000 light years, then a signal sent from A on the first day of its technological era would not arrive at B until 40,000 years after B has gone silent. The windows overlapped in time, but the distance ensured the signal arrived too late. They coexisted and still never knew. The researchers who studied this problem found that for contact to be probable, civilizations must not only overlap in time but also be spatially close enough that the light travel time between them is shorter than their shared active window. In a galaxy 100,000 light years across, this creates an extraordinarily narrow corridor of possibility. Two civilizations, both active for 10,000 years, would need to be within 10,000 light years of each other for even one exchange to be possible. The volume of the galaxy contained within 10,000 light years of any given point is a small fraction of the total. The odds shrink accordingly. Layer these constraints and the probability of contact does not just decline, it drops through the floor. You need civilizations to exist. You need them to develop technology. You need them to last long enough. You need them to overlap in time. You need them to be close enough for signals to travel within their shared window. You need the signals to be strong enough to detect. You need the receiver to be listening on the right frequency. You need the receiver to recognize the signal as artificial. Every one of these requirements is an independent filter, and the probability of passing all of them simultaneously is the product of their individual probabilities multiplied together. When each one is less than certain, the combined probability becomes vanishingly small, and all of the above assumes that we would recognize a signal if one arrived. The search itself faces a combinatorial problem so vast that even framing it accurately requires stepping back from the familiar narrative of radio dishes scanning the sky and looking at the actual mathematics of what a comprehensive search would require. A radio telescope searching for an alien signal must make choices along three independent axes: direction, where in the sky to point; frequency, which channel to listen on; time, how long to dwell on each target. Each axis contains an enormous number of possibilities, and the total search space is the product of all three. Start with direction. The sky, as seen from Earth, can be divided into roughly 41,000 square degrees. A large radio telescope like the ones used by the Breakthrough Listen project has a beam width of a few arc minutes, meaning it observes a patch of sky roughly 1/2000th of a square degree at a time. To cover the entire sky at that resolution would require tens of millions of individual pointings. Each pointing must be held long enough to accumulate a detectable signal, which, for a faint source, thousands of light years away might mean minutes or hours of integration time. A complete scan of the full sky at a single frequency would take years of continuous observation. Now add frequency. The radio spectrum usable for interstellar communication spans roughly tens of gigahertz. Current search systems divide that range into narrow channels, each one a few hertz wide, and check each channel independently for artificial patterns. The number of individual frequency channels across the full usable spectrum is in the billions. Each one must be checked at each pointing. Now add time. A signal that is present for only a brief period, either because the source is transient, because the transmitter is rotating, or because the beam sweeps past our direction, could be missed entirely if we are not observing that patch of sky at the right moment. The signal might last for seconds, or minutes, or hours, and we have no way of knowing in advance when to look. The total search space is direction multiplied by frequency, multiplied by time. The resulting number is not just large, it is astronomical in the most literal sense of the word. A study published by researchers at Penn State attempted to quantify how much of this search space humanity has actually explored. Their analogy was vivid and painful. Imagine the total search space as the volume of Earth's oceans. Every ocean, every sea, every body of salt water on the planet. The portion we have searched so far is equivalent to roughly the volume of a large swimming pool. Perhaps a hot tub. That is not a failure of effort. It is a consequence of the mathematics. The search space is so immense that even a century of dedicated observation, using the largest instruments humanity possesses, covers a fraction so small that it barely registers. We have not searched the ocean and found it empty. We have scooped a single glass of water from the Pacific, examined it, found no whales, and begun to wonder whether the ocean is lifeless. The combinatorial explosion means that dramatically increasing our search capability does not proportionally increase our coverage. A telescope 10 times more sensitive does not search 10 times more of the space. It extends the detection range by a modest factor, which increases the volume covered, but the frequency and time dimensions remain unchanged. A truly comprehensive search of even the nearest few thousand stars across the full usable frequency range would require resources that exceed anything currently funded by orders of magnitude. This is not an argument against searching. It is an argument for humility about what the silence means. The absence of a detected signal, given the tiny fraction of the search space we have covered, cannot be taken as evidence that no signal exists. It can only be taken as evidence that we have not yet looked in the right place, at the right frequency, at the right time. The haystack is galactic in size. The needle, if it exists, could be anywhere within it. And we have examined a single straw. But let us set aside the statistics for a moment and ask a more visceral question. How long do civilizations actually last? We have exactly one example. Hours. And our track record is not encouraging. Modern human civilization, defined as the period since the development of agriculture, large-scale settlement, and written language, is roughly 10,000 years old. Technological civilization, defined as the period since the Industrial Revolution, is roughly 250 years old. The period during which we have been capable of interstellar communication is roughly 100 years old. In that brief window, humanity has come within minutes of nuclear annihilation on multiple documented occasions. The Cuban Missile Crisis in 1962, the 1983 Soviet early warning system false alarm, where a single officer's judgment call prevented a retaliatory strike based on faulty satellite data. These events were not prevented by wisdom or planning. They were prevented by luck, by the individual judgment of specific human beings in specific moments, any of whom could have decided differently. Nuclear weapons are not the only existential risk. Climate disruption is altering the planet's systems on a timescale of decades. Engineered pathogens could emerge from laboratories or from deliberate design. Artificial intelligence systems are advancing toward capabilities whose long-term implications remain deeply uncertain. Resource depletion, ecological collapse, and the cascading fragility of interconnected global systems all represent pathways by which a technological civilization could lose its capacity to communicate with the stars. And these are just the risks we can identify from our own experience. A civilization on another world would face its own unique set of threats, shaped by its biology, its environment, its psychology, and its history. Some of those threats might be ones we cannot even imagine, emerging from the specific evolutionary path of a species whose mind and motivation bear no resemblance to our own. The point is not that civilization always destroys itself. The point is that maintaining a technological civilization is hard. It requires continuous energy input, institutional stability, resource management, and the avoidance of both natural and self-inflicted catastrophes across timescales that grow longer as the civilization grows more complex. And the longer the required timescale, the more opportunities there are for something to go wrong. A civilization that lasts 1,000 years has to survive everything that can go wrong in 1,000 years. A civilization that lasts 10,000 years has to survive 10 times as much. A civilization that lasts 1,000,000 years, the kind of duration needed for interstellar travel at any realistic speed, has to survive asteroid impacts, supervolcanic eruptions, stellar flares, ice ages, pandemics, internal conflicts, technological accidents, and every other threat that a planet and a species can throw at a complex technological system across a span of time longer than our entire species has existed. The geological record of Earth makes this vivid. In the last 500 million years, there have been 5 mass extinction events, each one destroying between 70 and 96% of all species alive at the time. The most recent, caused by the Chicxulub asteroid impact 66 million years ago, wiped out the dinosaurs and roughly 75% of all species on the planet. If a technological civilization had existed among the dinosaurs, it would have been annihilated along with them. 100 million years of evolutionary progress erased in a geological instant. These events are not rare anomalies, they are regular features of planetary history. On a timescale of tens of millions of years, mass extinctions are expected. They are part of the normal operating rhythm of a geologically active world orbiting a star in a galaxy full of debris. Any civilization hoping to last long enough to cross the gaps between stars must survive not just its own internal challenges, but the external violence of a universe that regularly resets the biological clock on planetary surfaces. And asteroids are not the only external threat a civilization must endure. The galaxy itself is violent in ways that operate on timescales perfectly calibrated to punish any species trying to last long enough for interstellar contact. Gamma-ray bursts are the most energetic explosions in the known universe. A long-duration burst, produced by the collapse of a massive star into a black hole, releases more energy in 10 seconds than our sun will emit in its entire 10 billion year lifetime. If such an event occurred within a few thousand light years of a habitable world, the burst would strip away a significant fraction of the planet's ozone layer within minutes, exposing the surface to intense ultraviolet radiation for years afterward, and triggering ecological damage that could take millions of years to recover from. Some researchers have proposed that a gamma-ray burst may have contributed to the late Ordovician mass extinction roughly 445 million years ago, one of the 5 great die-offs in Earth's history. These events are not predictable. They are not preventable. A civilization cannot see a gamma ray burst coming because the burst itself travels at the speed of light. The first warning is the arrival of the radiation. By the time you know it has happened, the damage is already done. Nearby supernovae pose a similar threat on a smaller, but still devastating scale. A supernova within roughly 30 light years of a habitable planet would deliver enough radiation to cause severe ozone depletion and elevated mutation rates across the biosphere. Statistical models suggest that a supernova occurs within that lethal radius of any given point in the galactic disk roughly once every few hundred million years. Over the billion-year timescales relevant to biological evolution, these events are not rare. They are periodic resets, random in timing, lethal in effect, and completely indifferent to whatever civilization might be flourishing on a nearby world when the star detonates. Even the host star itself can betray its planets. Stellar flares, sudden eruptions of magnetic energy from a star's surface can bombard orbiting worlds with bursts of radiation and charged particles. Our own sun produces flares, though most are modest. Red dwarf stars, the most common type in the galaxy and the type most likely to host rocky planets in their habitable zones, are far more active. Proxima Centauri, the nearest star to ours and the host of at least one planet in its habitable zone, is a known flare star that produces eruptions powerful enough to sterilize the surface of any unshielded world orbiting it. A civilization does not get to choose whether its star flares, whether a nearby star explodes, or whether a gamma ray burst from across the galaxy happens to be pointed in its direction. These hazards are external, random, and governed by astrophysics rather than by any decision the civilization makes. They represent a category of fragility that cannot be engineered away, only endured. And enduring them requires lasting long enough on a planetary surface exposed to a galaxy full of energetic violence to still be broadcasting when someone finally listens. And survival is not the same thing as continuity. A civilization can survive in the sense that the species persists without surviving in the sense that its technology, its institutions, and its capacity for interstellar communication remain intact. History is full of examples where complex societies collapsed, not into extinction, but into simpler forms that lost capabilities their predecessors had achieved. The Roman Empire did not go extinct, its people survived. But the roads, the aqueducts, the legal systems, and the administrative networks that defined it as a civilization disintegrated over centuries. Knowledge was lost, capabilities were forgotten. If a technological civilization suffers a collapse of this kind, its window of detectability closes. It may still exist as a biological species, but it is no longer broadcasting, no longer listening, no longer participating in the interstellar conversation. From the perspective of any other civilization trying to find it, it has gone silent. It might as well not exist. This introduces a concept that is rarely discussed in popular treatments of the Fermi paradox, but that is central to the actual probability calculation: the communicative lifespan. This is not how long a species survives. It is how long a species maintains the specific capability and motivation to engage in interstellar communication. And it may be much shorter than the species' biological lifespan. That gap between biological existence and technological capability defines a concept central to the contact problem and rarely discussed in popular treatments of the Fermi paradox: the communicative lifespan. If we destroyed our technological infrastructure tomorrow through war, environmental collapse, or any other mechanism, but the species survived, we might endure for hundreds of thousands of additional years as a pre-technological population, biologically alive, culturally active, but invisible to the galaxy. Hundreds of millennia of biological existence bookending a sliver of technological visibility. The ratio between the two could easily be 3,000 to 1 or higher. If that ratio is typical, if most civilizations burn brightly for a brief technological moment and then fade back into biological anonymity, then the galaxy could have produced millions of intelligent species across its history, each one blinking on and off like a firefly, each one visible for an instant against the vast dark of cosmic time. And just as a field full of fireflies can appear empty if each one flashes too briefly and too rarely for any two flashes to overlap, a galaxy full of short-lived civilizations can appear silent even though the total number of civilizations across all of history is enormous. There's another dimension to the timing problem that compounds all of the above. It concerns not just when civilizations exist, but how they change while they exist. A civilization capable of interstellar communication in its early technological phase may not remain interested in interstellar communication as it matures. Human history shows that the priorities of a civilization shift dramatically over time. The questions that obsess one generation are irrelevant to the next. The technologies that define one era are abandoned in the next. A civilization that begins by broadcasting radio signals into space might, within a few centuries, transition to communication technologies that are invisible to radio telescopes. Tightly beamed laser transmissions, quantum encrypted channels, information architectures that we cannot even conceptualize, because they depend on physics we have not yet discovered. If a civilization's communication technology evolves past the point where its signals are detectable by a younger civilization's instruments, the older civilization effectively disappears. It still exists. It may be thriving, but it is broadcasting on frequencies or through media that the younger civilization does not know how to receive. The conversation fails not because no one is talking, but because the languages have diverged past the point of mutual recognition. This is not speculative. It is the trajectory of our own technology. In the 1950s, Earth was a relatively bright radio source, leaking high-powered television and radar signals in all directions. Today, communication has shifted increasingly toward fiber optics, which leak nothing into space, and toward low-powered digital signals spread across wide frequency bands, which are much harder to distinguish from noise at interstellar distances. If the trend continues, Earth's radio signature will fade over the coming century. We will become quieter, not because we failed, but because we succeeded. Our technology will have evolved past the point where it is visible to anyone listening with the kind of equipment we ourselves used a generation ago. But technology is not the only thing that evolves. The species itself changes. And this introduces a dimension of the timing problem that has almost nothing to do with engineering and everything to do with biology. Evolution does not stop when a species becomes intelligent. It slows in certain directions, particularly once a civilization develops medicine and reduces the selective pressure of disease and predation. But it does not halt. Over timescales of tens of thousands of years, genetic drift, sexual selection, adaptation to changing environments, and the accumulation of mutations continue to reshape the species. Over hundreds of thousands of years, the changes become significant. Over millions of years, they become transformative. Consider what a million years of continued evolution would do to a species that began at roughly our level. A million years ago, our ancestors were Homo erectus, a species with a brain roughly 2/3 the volume of a modern human's. The cognitive and physiological differences between Homo erectus and Homo sapiens are profound. If Homo erectus had built a radio telescope and broadcast a signal, modern humans receiving it would be decoding a message from a mind so different from ours that the very concept of communication might not translate. Now project that forward. A technological civilization that survives for a million years does not remain the same species that built its first transmitter. Its nervous system will have changed. Its sensory apparatus will have changed. Its motivations, its social structures, its cognitive architecture, all of these are products of biology, and biology does not hold still. After a sufficient span of time, the evolved species might no longer perceive the electromagnetic spectrum in the same way. It might have shifted its primary sensory channels to modalities that have no equivalent in our biology. It might communicate through chemical signaling, or through direct neural coupling, or through mechanisms that arise from biological structures we have never encountered. The idea of broadcasting a radio signal into space might be as alien to this evolved species as echolocation is to a human. Not impossible to understand in the abstract, but utterly foreign as a natural behavior. There is a deeper implication. A species that has evolved for a million years may no longer want what we want. The drive to explore, to communicate, to find others, these are products of our specific evolutionary history, shaped by the social pressures and survival challenges of the African savanna over the last few 100,000 years. Curiosity, loneliness, the desire for connection, these feel like universal drives, but they are not. They are features of human psychology, sculpted by natural selection under conditions that are specific to our lineage. A species whose evolutionary path was shaped by different pressures. A deep ocean world where isolation was the norm. A world with no predators where cooperation never conferred a survival advantage. A world where the dominant sensory channel was chemical rather than visual, might develop intelligence without developing any inclination to search for others. The question, is anyone out there, might never occur to them. Not because they are less intelligent, but because their intelligence was built by a different set of pressures and aimed at a different set of problems. Even within our own species, the drive to search for extraterrestrial intelligence is not universal. It is concentrated among a small number of scientists and enthusiasts. The vast majority of humanity has never spent a single moment wondering whether anyone is listening from the stars. If that indifference is the norm among intelligent species rather than the exception, then the galaxy could be populated with minds that have no interest whatsoever in the question we find so compelling. They are intelligent, they are complex, they may have built vast civilizations, and they have never once looked up. If this pattern is typical of technological civilizations generally, it creates a paradox within the paradox. The civilizations most likely to be detectable are the youngest ones. The ones still using crude, leaky, high-power broadcast technologies. The older and more advanced a civilization becomes, the harder it is to find. The very process of technological maturation makes civilizations invisible. Combine this with everything else: the brevity of technological windows, the fragility of complex societies, the distance-time interaction that requires civilizations to be both close and contemporary, the signal degradation over interstellar distances, the evolutionary drift of communication technology toward invisibility, the geological and cosmic hazards that periodically reset planetary surfaces. Each of these factors independently reduces the probability of contact. Together they do not add, they multiply. The combined probability is the product of all their individual probabilities, and when you multiply a series of small numbers together, the result is not just small, it is microscopic. This is the compound barrier. No single factor makes contact impossible. No single wall is impenetrable, but the walls are stacked. They stand one behind another, each one filtering out a fraction of the possibilities that survived the one before it. Distance eliminates the civilizations that are too far away. The speed of light eliminates the ones whose signals cannot arrive in time. The timing filter eliminates the ones that did not exist during our window. The fragility filter eliminates the ones that did not survive long enough to finish their message. The technology filter eliminates the ones whose communication evolved past the point of detectability. And what remains after all those filters have done their work may be nothing. Not because the universe is empty, because the universe is a series of sieves, and each one is fine enough to catch nearly everything that passes through the one above. The galaxy may have produced 1 million civilizations across its history. It may be producing new ones right now, at this very moment, on worlds we have not yet discovered, around stars we have not yet catalogued. The universe may be alive with intelligence, teeming with it, saturated with curious minds looking up at the same sky we look at and asking the same question we ask. And none of them can reach each other, not because the walls between them are new, not because the walls are temporary. The walls were there before the first star ignited. They are not temporary obstacles waiting to be outgrown. They are permanent features of the universe, as old as the cosmos itself and as unyielding as gravity. They are consequences of the speed of light, the age of the cosmos, the thermodynamics of signal propagation, and the fragility of complex systems operating on a planet's surface. They are not obstacles to be overcome. They are features of the architecture. What remains is the deepest question of all. Not whether we are alone, not whether the barriers can be broken, but what it means to live in a universe that may have been built, not by any mind, but by the blind operation of physical law to keep its inhabitants permanently apart. That question, and the answer that emerges from it, is where this story ends. We have walked through the walls one at a time. Distance, speed, time, fragility, signal decay, technological drift. Each one, taken alone, makes contact harder than most people realize. Taken together, they do something worse. They make contact not merely difficult, but structurally improbable. Not because of any single impassable barrier, but because the barriers are layered so deeply and so tightly that the space left between them, the narrow corridor through which contact would have to pass, may be too thin for anything to fit through. But we have not yet asked the question that matters most. We have described the locks, we have measured the walls, we have counted the filters. Now we need to step back and look at the building itself. Not at any single obstacle, but at the totality of the structure. Because the deepest answer to the Fermi paradox is not about any one barrier. It is about the architecture. The universe is not a room. It is not an arena. It is not a neighborhood or a network or a web of connected points through which sufficiently clever travelers can navigate. The universe is a structure, and that structure has a shape, and the shape has consequences for everything that lives inside it. Start with the geometry. Space is three-dimensional. When you double the radius of the sphere you are searching, the volume inside does not double. It increases by a factor of 8. Triple the radius, and the volume increases by a factor of 27. The amount of space that must be searched grows cubically with distance, while the strength of any signal crossing that space diminishes with the square of the distance. Volume grows faster than reach. This is not a problem that technology solves. It is a geometric property of three-dimensional space. A civilization with a transmitter 1,000 times more powerful than ours does not reach 1,000 times farther. It reaches roughly 32 times farther, because the inverse square law dictates that signal strength drops with the square of the distance. 32 times farther is meaningful, but in a galaxy 100,000 light years across, it is not enough. It is never enough. The geometry always wins. Now add the temporal dimension. The galaxy is not a snapshot. It is a film running for 13 billion years. Civilizations do not all appear in the same frame. They appear in scattered frames throughout the film, each one visible for only a handful of frames before fading. The probability of two civilizations sharing the same frame and being close enough in space for a signal to travel between them during their shared screen time is governed by the same punishing arithmetic we explored earlier. Time multiplies the isolation that distance creates. The two dimensions of separation, space and time, do not merely coexist, they compound. A civilization that is close in space but distant in time is just as unreachable as one that is close in time but distant in space. And a civilization that is distant in both is unreachable twice over. This compounding is the key insight. The Fermi paradox is usually discussed as if it were a single question with a single answer. Are they hiding? Are they dead? Are they too far away? Are they too different? Each proposed solution addresses one barrier. But the real structure of the problem is not a single wall. It is a maze with walls in every direction, each one independent of the others, each one filtering out a different subset of possible contacts. To pass through the maze, a civilization must clear every wall simultaneously. It must exist at the right time, in the right place, with the right technology, at the right stage of development, with signals strong enough to cross the distance, aimed in the right direction, on a frequency the receiver can detect, during a window when the receiver is listening, and before either civilization ceases to exist. Each individual wall might be passable, the odds of clearing any one of them on its own might be reasonable, even encouraging. But the walls are not encountered one at a time. They are encountered all at once, and odds that seem manageable in isolation become something else entirely when they must all be beaten simultaneously. 10 barriers, each with a 10% chance of being cleared, do not produce a 1% chance of total success. They produce a 1 in 10 billion chance. The numbers do not add, they cascade. And this cascade is not a pessimistic assumption. It is a mathematical consequence of independent filters applied in sequence. The universe does not need to be hostile to produce silence. It does not need to contain a single catastrophic great filter that destroys all civilizations at a specific stage. It only needs to contain many moderate filters, each one survivable on its own, that together reduce the probability of contact to a number so small it is functionally zero. This is the architecture of silence. Not a wall, not a trap, not a predator, a structure, a geometry of separation woven into the fabric of the universe at every level. From the speed of light, to the expansion of space, to the thermodynamics of signals, to the fragility of complex systems, to the finite duration of technological windows. The silence is not evidence of absence, it is evidence of architecture. And here is where the implication becomes genuinely unsettling. Because if the silence is architectural, it does not depend on whether life is rare. It does not depend on whether intelligence is common. It does not depend on whether civilizations tend to destroy themselves. The silence holds even in the most optimistic scenario imaginable. Imagine a galaxy teeming with life. Billions of habitable worlds, each producing its own biosphere. Intelligence arising on millions of those worlds. Civilizations building telescopes, broadcasting signals, searching for others with the same desperate curiosity that drives us. Even in that universe, the architecture of separation does its work. The civilizations are scattered across a disk 100,000 light-years wide and 13 billion years deep. Each one lasts for a few thousand years, maybe a few tens of thousands, if it is unusually resilient. Each one broadcasts signals that weaken and become undetectable within a few hundred light years. Each one searches a tiny fraction of the sky on a narrow band of frequencies for a brief window of time. Each one faces the compound probability of overlapping with another civilization in both space and time, with signals strong enough to bridge the gap, during a window when both are listening. Run the numbers with generous assumptions. Millions of civilizations across the galaxy's history. Long lifespans. Powerful transmitters. Sensitive receivers. The compound probability of any two of them making contact still collapses under the weight of the filters. The galaxy is alive, crowded, buzzing with intelligence, and every single civilization in it dies without ever confirming that any of the others existed. That is the scenario that should keep you awake. Not an empty universe, a full one. A universe rich with life, saturated with intelligence, populated by civilizations that wandered and searched and hoped and listened. And every one of them heard nothing. Not because no one was there, but because the structure of reality placed them too far apart, in time or in space or in both, for any signal to arrive while anyone was still listening. The universe did not forget to connect them. It was never wired for connection in the first place. The same physics that allowed stars to form, that allowed chemistry to complexify, that allowed biology to emerge and intelligence to develop, also created the distances between stars, the speed limit on information, the expansion of space, and the entropic decay of every signal ever sent. The universe built the minds and then built the walls between them using the same laws for both. This is not a malicious design. There is no intent behind it. The universe is not cruel. It is indifferent. The laws of physics do not care whether civilizations meet. They produce stars and planets and chemistry with the same mechanical consistency with which they produce light years and signal decay and cosmic expansion. The ingredients for life and the barriers to contact are not separate features of reality. They are the same feature, viewed from different angles. Consider the speed of light itself. It is not merely a speed limit. It is the rate at which electromagnetic fields propagate, the rate at which gravity transmits its influence, the rate at which cause and effect unfold. Without it, Atoms could not form. Chemistry could not operate. Stars could not burn. Biology could not exist. The speed of light is not an obstacle placed in the path of civilizations seeking contact. It is a prerequisite for the existence of civilizations in the first place. The very constant that makes life possible is the same constant that makes contact nearly impossible. The wall and the foundation are the same thing. The same is true of cosmic expansion. The stretching of space that carries galaxies beyond the cosmic horizon is driven by the same physics that governs the large-scale structure of the universe, the distribution of matter, the formation of galaxy clusters, the web of filaments and voids that shapes the cosmos. Without expansion, the universe would have collapsed back into a singularity long ago, or remained a featureless soup of radiation. Expansion is what gave matter room to cool, to clump, to form stars and planets and the conditions for life. And expansion is what carries most of the universe permanently beyond reach. The mechanism that created the arena is the same mechanism that makes the arena too large to cross. There is a way of seeing this that transforms the Fermi paradox from a question into a statement. The paradox asks, where is everybody? The architecture answers, everywhere. Everywhere and unreachable, not missing, not hiding, not dead, present and separated, present and isolated, present and silent, because the silence is not a choice or a failure or a tragedy. It is a property of the medium in which everyone exists. Think of it this way. Sound cannot travel through a vacuum. This is not because sound is weak or because vacuums are hostile. It is because sound requires a medium, air or water or solid matter, to propagate, and a vacuum contains no medium. You could scream at the top of your lungs in the vacuum of space, and a person floating 1 meter away would hear nothing. Not because they're deaf, not because you're quiet, because the physics of the situation does not permit the transfer. The universe may be the equivalent of a vacuum for civilizations. Not because it contains no medium for signals. Electromagnetic radiation travels through vacuum just fine. But because the combination of distance, time, signal decay, expansion, and civilizational brevity creates a situation where the effective transfer of meaningful contact between civilizations is not supported by the medium in which they exist. The signals exist, the civilizations exist, but the connection does not form because the parameters of the medium do not allow it to form, not for any one fatal reason, but because the aggregate of all the parameters falls below the threshold required for contact to occur. This framing changes the emotional weight of the question. If the silence is caused by a single catastrophic filter, a great filter that destroys civilizations at a specific stage, then there is hope in identifying and avoiding it. If the silence is caused by deliberate hiding, as in the dark forest theory, then there is hope in finding the hidden. If the silence is caused by rarity, then there is hope in being special, in being the one miraculous exception. But if the silence is architectural, there is no single thing to fix. There is no wall to break through. There is no enemy to defeat. There is no test to pass. The silence is a consequence of the shape of the universe itself, and the shape of the universe is not something a civilization can change. You cannot repeal the speed of light. You cannot reverse the expansion of space. You cannot compress the age of the galaxy into a window narrow enough for civilizations to overlap. You cannot make signals stronger than the inverse square law allows. You cannot make civilizations last longer than the accumulated hazards of a planetary surface permit. Each of those limits is grounded in physics, tested and confirmed to extraordinary precision. Together, they define a universe in which the default state of intelligent life is isolation, not loneliness by choice, isolation by structure. This brings us to the final and most profound implication, the one that sits at the center of everything this story has been building toward. The most unsettling possibility is not that the universe is empty. An empty universe would be sad but simple. We would be alone, and we would know it, and we could make our peace with it. The most unsettling possibility is that the universe is full of life, full of intelligence, full of civilizations that built telescopes and libraries and philosophies, full of species that looked up at the sky with the same wonder we feel and asked the same question we ask. Where is everybody? And every single one of them received the same answer: silence. Not because no one was out there, because the architecture of reality ensured that the question could never be answered. The distances were too great. The signals were too weak. The windows were too brief. The timing was too scattered. The barriers were too many, too deep, too tightly layered for any signal, any ship, any message to thread the gap between one island of intelligence and another. A universe full of voices, none of which can hear each other. A cosmos saturated with minds, each one confined to its own small volume of space and its own brief moment of time, separated from all the others by walls that are not made of stone or metal, but of light years and millennia, and the geometry of expanding space-time. That is the architecture of silence, and it is not a theory about what might be true. It is a description of what the known laws of physics produce when you apply them honestly to the question of whether civilizations can meet. They probably cannot. Not because the universe is hostile, not because there is a predator lurking in the dark, not because civilizations inevitably destroy themselves, not because intelligence is rare, but because the structure of reality, the same structure that allows stars to form and planets to cool and chemistry to become biology, also places those planets so far apart, in spaces so vast and across timescales so long, that the civilizations they produce are born, live, and die without ever confirming that any other civilization ever existed. The silence is not empty. It is full of voices that will never reach each other. And we are one of those voices, speaking into a cosmos that may be crowded with listeners, every one of them too far away, or too early, or too late, or too brief to hear us. We search the sky and find nothing, and we conclude that the universe must be empty. But the universe may not be empty. It may simply be built in a way that ensures we will never know. That is the real reason alien contact may never happen. Not because nobody is out there, because the universe may be full of somebody, and the laws of reality keep every one of them apart. We are surrounded by stars, trillions upon trillions of them, many of them older than ours, many of them circled by the worlds where perhaps someone once looked up, someone built something, someone wondered. We will probably never know their names, not because they did not exist, because the universe in all its vastness, in all its beauty, in all its terrifying indifference was never built to let us meet. The silence is real, and it may be permanent, and the hardest truth of all is that it might mean the opposite of what we always assumed. The silence does not mean we are alone. It means we may never find out whether we are or not. And that, in the end, is the loneliest answer of all.